My name is Tamitha Mulligan-Skov, and I will come out of the gate saying, I know you guys are going to flip through your books a little bit. This presentation has been altered a little bit since print, and the reason for that was because the week that I had to get this ready for print was the same week that the Space Weather Prediction Center, NOAA's center, were having their space weather, oh, sorry, should I have stood on the other side? I'm going to drive him crazy because now I'm going to walk over here. No, there's the same week that the Space Weather Prediction Center was having their annual space weather workshop. And in this particular space weather workshop came all of the solar scientists that are doing all the predictions for solar cycle 25. And so I was completely mad and had all the colleagues I could who were going there go up with their cell phones, sit in the front row and take snapshots. So if you guys have looked at your book and looked at the pictures of a couple of my slides, you'll see those were cell phone pictures of those slides. And I've modified them, and I've also added a little bit because I wasn't super excited about their findings, and we'll get into that. But at any rate, in case you're wondering why these slides will be slightly different as we get near the end, that is why. So, okay, good. So I always like starting out because I kind of do a right turn compared to pretty much all the other talks in this venue. So I want to remind everybody about space weather, what it is. I will no longer ask anyone the question of what is space weather. The last time I was here, I did that. Every hand in the room went up. So I figured by now you guys probably have an idea of who I am and what I do and why I'm here helping you guys. But what I do want to remind you of is that space weather isn't just about space weather here at Earth and how it affects ham radio here on Earth. And there's a real reason for this, that I'm going to point out the fact that basically space weather is a planet's interaction with its host star and the surrounding space environment. And you can see I've got a lot of other planets here, and none of them are Earth. And I'll get to that in just a second. Because more generally it occurs at planets, moons, comets, asteroids, and other celestial bodies in the universe. We see, for example, aurora at planets. Here's Saturnian aurora. Here's Jovian aurora. For Jupiter, you can see how amazing Jupiter's aurora is. You can actually see planets, its moons. That's Io, that's Callisto, I think, and Ganymede. And they're coupled magnetically to the planets, so they get really cool aurora, going on. The reason why I'm showing you all of this is that we plan to go to Mars very soon. And Mars is a planet, right? And Mars has space weather, right? And Elon Musk, despite numerous attempts to slow him down, is hell-bent on getting people to Mars, either near Mars or by Mars or on Mars, by something like 2032, as we get through this swing by, or basically our closest approach. It actually makes the transit time between Earth and Mars the shortest. And that's what everybody seems to be worried about, is just the transit time between Earth and Mars, because we worry about cosmic rays and can we keep our astronauts safe. All right, that's wonderful. But just like campaigning for the presidency, everybody thinks about the campaign. They never think about what they do once they get elected. Once we get to Mars, how are we going to survive, right? Mars does not have an atmosphere or a magnetic shield like Earth does. It's a lot more susceptible to space weather. And just like we colonized Earth many years ago, before we had these wonderful devices, right? What did we use to talk over the horizon? You guys use it? Maybe you know what that is? Somehow I have a feeling you might know. Well, the Mars generation, which is a generation that's coming up through the ranks now and only knows Elon Musk, right? They probably want Elon Musk to run for president. These guys know cell phones. They grew up with this. They're called technology natives. This is what they think is real, and they think they can take this to Mars. So, Earth colonists, you guys are Elmers to the Mars generation, okay? And I don't take that lightly. So anybody who tells you that amateur radio is a dying art, pop them once for me and say, that's from Tamitha Mulligan-Skov. Okay? Ham radio is the future, not the past, and we need to think like that because it's coming. The future is coming faster than we want to believe it will. Okay? So that's why I do this. So just to kind of remind you, the basic types of solar phenomena affecting Earth, we have solar flares. This is when the sun screams, and I'll see if I can play this little movie. I'm sure you guys know what a solar flare looks like, but there you go. That's the sun screaming. And radio bursts happen all the time with that type of stuff. Happens very quickly, and it affects Earth in a very particular way. See if I can turn it off. Here's a coronal mass ejection, also called a solar storm. It's much slower, oftentimes happens with solar flares, but not all the time. Takes about 4 days to get to Earth, a lot more material there. This is what hits Earth and causes aurora, which means auroral propagation. So instead of frowning with these types of events, you can sometimes smile with those, because that actually means propagation, where this means death for propagation. We also have solar radiation storms, right? And that's the high latitude stuff. That's driven by both of these. And you get that at high latitudes and low latitudes mostly. This is due to a solar flare. But that can kill radio propagation. And then we also get coronal holes. We get fast wind from coronal holes. That's this dark area here. And that drives fast solar wind that kind of mimic these structures when they hit Earth. They can cause solar storms and give you more aurora. But that's really not why we're here today. We're really here, hello? We're really here to, as a matter of fact, I shouldn't do that because I think my ringer's on too. My bad. Okay, so really why we're here is to talk about the upcoming solar cycle, right? Well, a lot of people like to think about the sun pretty much as like a light bulb in the sky. It doesn't change all that much. But honestly, the sun is constantly changing. You can think of it as a giant fusion reactor that drives space weather, and its dynamics are very much like a lava lamp, believe it or not. Magnetically, it's very much like a lava lamp. So when you turn a lava lamp on, it can be kind of quiet, and then once it heats up, now you got bubbles of stuff everywhere. Some are floating, some are sinking, and that's exactly what happens on the sun all the time. And this type of dynamics give us a ton of energy output. We have electromagnetic radiation from X-rays all the way down through radio waves. That you know because you guys deal with radio waves all the time. You hear the sun constantly. Someone told me that the sun is the biggest HF generator that God ever made, at least in our solar system. We have the solar wind that comes with plasma and magnetic field, and that can cause us problems. Of course, we have solar flares, where that causes radio blackouts. We have solar energetic particles, they call them SEPs in science vernacular, but that's radiation storms. And then we have coronal mass ejections, we also call those solar storms, and that causes auroral propagation, causes problems on the bands on the night side, causes fun for the gray line, all sorts of crazy stuff. Now, because we have all this type of energy coming out, we have to look at the sun in so many different colors. You'd think that every time you see these things, you're like, why are the scientists looking at the sun in this color or that color? Are they bored? I mean, why do they do this stuff? Honestly, you may not believe it, but this set of pictures has been taken at essentially the same time. Pretty hard to believe, right? This is the white light image, what you see on the ground with your eyes. It shows sunspots, the dark areas, right? But as we go up in energy and up in outer space, because you can't see this stuff without going into outer space. Our atmosphere actually blocks it. That's why you never see this stuff on the ground with a telescope. You have to go to space telescopes. But as you go higher in energy, now you're getting away from the sunspots, but you're actually seeing the Plages, the bright areas, and I'll talk about those more. You go a little bit higher, you're in the solar atmosphere almost. Now you see things like coronal mass ejections. Don't see them here, do you? Right? That's that same loop I showed you before. A little bit higher, now you're in the solar atmosphere. Now you see things like coronal holes, which you don't see here, but you see it here. But look, that solar storm, that CME is gone. You go higher in energy, you can see magnetic field, and you can see some of the activity in the waves that propagate across the sun. That's very important for scientists so that we know how big an eruption is on the sun. You can see like solar earthquakes, almost. And then as we go even higher, you get back to the bright areas, but now this is where we see the solar flare stuff. And you see a little bit of that loop from here. So that proves that I am talking about the same period in time. But the sun looks very, very different. And the reason why is that we have to peel the sun like an onion, like the layers of an onion to understand it. And for us scientists, well, color is the easiest way to do that. Someone says, well, what's the blue sun? I go, 131 angstroms. Well, what's the bronze sun? 193 angstroms. What's the red sun? 304 angstroms. I know immediately from the color what I'm looking at. Now, you'd think that the scientists would be smart enough to keep the colors standardized between the spacecraft. No. So just in case you think you're going to get savvy and say, okay, well, I'm going to look at the green sun from SOHO. Well, it may not be the same as the green sun from STO, so you got to be a little careful. Anyway, so let's focus on sunspots. Everybody knows sunspots, right? I mean, that's one of the main reasons or main ways that we take a look at space weather, especially as amateur radio operators. We look at sunspots, we look at solar flux, and those are pretty much the two main proxies of solar activity. Well, I'm going to kind of blow away a few of the myths and issues that we have with being so oversimplifying the idea of solar activity from this point of view. But to do that, I have to talk about what sunspots actually are. So here's a nice sunspot, and obviously you notice that it's very, very dark in the middle. It's a little bit lighter on the outside, and then it's very, very light. Well, remember I was talking about the sun being pretty much like a lava lamp, right? Think of it almost as if it's like a boiling lava lamp or a boiling pot of hot water. It's bubbling up to the surface all the time. And when there's stuff bubbling up to the surface, it's emitting light. You're getting radiation. So this is the light that comes up to the surface. That's what all this stuff is. It essentially looks like a big boiling pot of hot water, okay? And as long as the pot is boiling, we don't have a problem. We see lots of light, right? We get lots of solar flux. But what is this mess? Well, think of it as like a submarine in the pot of boiling water. If it begins to rise and pop through the surface, suddenly it disrupts that boiling, and that's the dark. No light, no boiling, no light, dark hole. It's not really a hole. It's just a lack of emission. It's because there's something blocking that boiling pot of stuff. Now, the stuff on the outside is, well, it's not quite as blocked, partially blocked, right? And this is actually part of like a tube. And so the way and this is all magnetic field. It's like a magnetic submarine that pops through the surface. And the reason why it does that is the same thing in the lava lamp. It gets buoyant and pops up through the surface. And then sometimes it'll recede back down and it'll pop up again. Periscope up, periscope down. Does exactly the same thing. And this is why we get sunspots that come up to the surface and then disappear again, sometimes without any notice at all. Now we can get all sorts of simple ones like this. We can get more complicated ones. I can call it by the scientific names if you want, the umbra and the penumbra, but it doesn't really matter. We can also get extremely complicated structures where you've got tons of these umbras, these dark areas, followed by lots of the lighter areas. But and the more complex they get, oftentimes magnetically, the more dangerous they are. But that's not really what we want to talk about. What we want to talk about is why do we have sunspots and why do they matter? Why are they proxies for solar activity? Well, honestly, it's all part of the solar magnetic dynamo. Now, we don't know as solar scientists much about the dynamo. I'm not going to play around and say that we have everything figured out. We're not even close. We can't probe the sun. There's a lot of part of the sun that we can't even see into. And we try to do it with helioseismology, but it's not all that easy. But basically what we know of the dynamo, there's basically two main effects. We have the omega effect and the alpha effect. And really what we're looking at here is magnetic field. So just like the magnetic field at Earth, we're going to start with a magnetic field that points from north to south, just like it has here on Earth, okay? But just like Earth, the sun is rotating. But here's the trick. The sun isn't what we call a rigid body. The sun is kind of liquid and gas, a plasma, magnetized gas, right? So it can rotate at different speeds at different latitudes. That causes lots of problems for us because we call it differential rotation. And so what it means is that in this case, the equator, the sun is rotating faster than it is at the poles. Well, that then begins to take these guitar strings and yank them, pulling them off to the side. And now, instead of having beautiful magnetic field that goes straight north and south, now we have field that's beginning to go sideways, right, toroidal. And as you wrap that just like a rubber band around the sun and around the sun and around the sun, then you get more and more of this wrapped effect. Well, that becomes unstable. And that's when this other effect comes in, and it begins to get kinked. When things kink, they then can reconfigure, release energy, and now you've got magnetic loops. Well, magnetic loops go up and down. Submarine, anyone? Remember the submarine? That's how we get sunspots. And if we do this enough, with enough frequency, with this effect still happening, eventually those up and down loops that are kind of looking north-south reform that magnetic field. But now the magnetic field, instead of pointing north-south, points south-north. That's a flip. So in a nutshell, in a very oversimplified fashion, there's the solar dynamo. Okay? Case closed, right? Not even close. Whoops, I guess I could use this. I keep forgetting I can advance with this. How do I advance? I forget. Off. There. Which way? There we go. Okay. So let's put the picture together. Now, let me ask really quickly, how many people have seen a butterfly diagram before? Okay, so that's some of you. Okay. So really, what a butterfly diagram is, and we talk about this in science all the time. What you see, they look like really pretty butterfly wings, right? What you're looking at is over time, this is 1960 up through wherever, this is past like 1990. What you're looking at is essentially the equator of the sun right here. And then you're looking at the northern latitude and then the southern latitude. So you're basically looking at the face of the sun over time and how it changes. And what is plotted here, believe it or not, are where the sunspots are seen. So over time, what happens is that sunspots will appear at high latitudes. The magic latitude is around 55 degrees. And over time, they migrate. So in other words, the sunspots themselves don't migrate down, but when you see them appear, and then they sink, and then the submarine reappears, it reappears at a lower latitude over time. And it disappears again, and it reappears at a lower latitude. And it just keeps doing that over time until you get down to really low latitudes, like right at the equator. And that is solar minimum. And then, pop, the new cycle, new sunspots appear at high latitudes. It's the new cycle. And they start doing the same thing. The submarine comes out, and it disappears, and then it comes out, and disappears, and comes out, and disappears. And the cycle repeats over and over and over again. Solar maximum is right about where you see these lines here. Okay, it's not right here. This is solar minimum, where things really change. Right here is solar maximum. This is where you get the most activity. But really, what's going on is you've got, if you take the sun apart, you've got these magnetic field lines, and this is that differential rotation I was telling you about. So you've got magnetic field that's all wound up like a big twine ball. And you've got circulation of all of that boiling water that kind of goes down here in the inside, goes down near the equator, and that's dragging all those magnetic field lines down close to the equator. And then as they pop up, they go back, it goes back north up in the higher altitudes. And so it's got this funky little pattern. And we've been able to figure out this pattern, but we don't know exactly how it works. But somehow, with all of this magnetic field tied up like this, we get these loops. This is one of the submarines popping its head out. And we get this kind of thing where you get sunspots that start up here, they disappear, and as time goes on, this circulation pattern drags them closer and closer to the equator, okay? And that is what we know of the solar dynamo, putting it all together. And that's looking at the, looking at the butterfly diagrams is how we follow it. Now, I know I mentioned this before, that this is the sunspot thing and that they're dark because of the magnetic loops, but I wanted to give you a better, closer idea or closer look at what's really going on. So and I know it says gas here, it should say plasma. I didn't make the slide, just use it. So this is the surface of the sun, and you've got a sunspot here and here, as you can see. And what I wanted to show you is that essentially the magnetic, the submarine is kind of a twofold thing. It kind of pops up over above the surface and then dives back down. And so you're not looking at only one hole, you're looking at two that are connected to each other. And the activity is happening down here. This down here is where it blocks all that pot of boiling water coming up. And where it blocks that pot of boiling water come up, that's where it's dark on the surface. It shows up as being dark. Where it's not blocking quite so much is where it gets a bit lighter. But you can think of this as almost like a tube, okay? And you can also think about something coming out above the sunspot, up higher. It's not all just what's happening right here and here. There's something else, this magnetic field, that's connecting these two regions. And remember, the magnetic field is really what we care about. I mean, sunspots are beautiful, but it's the magnetic field that drives them, and it's the magnetic field that drives solar activity. So when you think of this, what it really does is it begins to beg the question of how sunspots really play the role of what we think, or do they play the role of what we think they do? Especially if they're dark, how in the world do they manage to affect the solar flux nearly like we think they do? And also, when we look at sunspots, we know when there are sunspots on the disk, the bands get noisy, right? There's radio noise coming from them. When there aren't any sunspots on the sun, things are reasonably quiet. When there are sunspots, it gets noisy. So we know they make a lot of noise, but they're dark. So how can they affect us this way? Well, the trick is understanding exactly what sunspots really are. Now, here's an example of, this is a white light image of the sun, and you can see a sunspot group here. Let's look at this sunspot group. Now, if you see this blue trace right here, do you notice this is brightness? And you notice as soon as this trace goes through this sunspot region, zoop, the brightness goes way down by about 0.34%. It's not huge, but in the measurement that it's made here is actually quite large. And this is because the sunspots they're visibly dark. So in white light, even in solar flux, they're dark. So why do we look at sunspots for solar flux? Does it make any sense? It shouldn't, but we do. And I'll show you why that's not very smart here in a minute. Now, we do care about sunspots when it comes to radio noise. And that is something we do need to pay attention to, because here's a bunch of sunspot groups in 14 gigahertz. This is done by the VLA radio telescope. And you can see it's an array, and you can see how incredibly loud they are with radio noise. So they may be visibly dark to the eye and dark in solar flux, but they are radio loud, and you can have both, of course, because they're different frequencies, right? So that hopefully will make you, get you to understand, because I have so many people ask me questions. If they're so dark, how can they be so loud? Well, this is how, because they're loud in different frequencies and quiet in different frequencies. But here's the real trick. When we looked at TRACE instrument, this is their TRACE spacecraft, we looked at some sunspots that were on the limb of the sun. You can see that sunspot right there. And this pattern shows the 8 gigahertz radio noise that was coming from the sunspot. Notice it's not on the sunspot at all. It's above it. Well, what does that mean? The radio noise comes from here. It's not coming from the sunspot, okay? What you're dealing with, again, is the magnetic field that causes the flares, the craziness, the solar dynamo, all of that stuff. Even at Earth, when you deal with space weather, what you're dealing with are magnetic fields reconfiguring, changing, releasing energy, and being noisy, having a big party while they're doing it. And that's why sunspots are radio loud. It's not the spot itself. It's actually what's going on with the magnetic field that you can't see. Now, what are sunspots? What are they not? They're not the source of flux, solar flux. But they're a proxy to some degree. It's kind of, it's like part of the story. Really, where the solar flux comes from are things called Plages, Faculae, and bright points. Now, what we have to do is just go back to that boiling pot of hot water. Remember what I was talking about, that the boiling pot allows all that emission to come out. And you're seeing it right here. You see these little bubbles, these little granules? These are bright spots on the walls of these granules. This is where all of that emission comes from. That is where the solar flux comes from. And you get them a lot of times near sunspots. See all this white stuff? See all the white stuff around here? All here and here? Those are faculae. Those are plages. That's where the bright stuff comes from. And that's because they trace sunspots to a great degree. That's why we actually get some solar flux. That's why we can actually use sunspots as a proxy. But there are times when there's no sunspot, and yet you have a ton of bright points. So keep in mind, I keep wanting to do that, I don't know why. So let me show you a different kind of butterfly diagram to extend this idea. Now this is from the Japanese Solar Science Observatory, and they've done this since, I think this is back from 1900 all the way to 2000. And what you're looking at here, I don't know if you can see this all this well, but this is these are the emissions from solar faculae, both in the northern hemisphere and in the southern hemisphere. But these here exclude this butterfly, okay? So if you see this butterfly diagram, this is the bright points. This is from all of the bright points, okay? And you can see that it does follow just like sunspot butterfly diagram does, except for one thing. What's this? What's this? What's this? What's this? And the same thing in the southern hemisphere. Notice that this side of the diagram gets lighter. It's because we had better observation techniques at that time. But you still see the same pattern. Now, even though overall these plages and bright points have a similar latitude distribution as the sunspots, and they can be used to determine solar cycle variability, we have been skipping out on the fact that some of these at the polar regions actually maximize during solar minimum. So you're actually right now at the peak of one of these sets of bright points near the poles. And these oftentimes are completely ignored. And they're definitely not captured when it comes to sunspot activity. So when you look at solar flux values and you look at sunspots and you try to say, okay, one should correlate with the other, they don't. Because with sunspots, they're only including the pattern that does this. They're not including what goes on at even higher latitudes. It's a habit. I give too many talks. I'll never break that habit, I'm sure. So really, when it comes right down to it, we look at sunspots and we look at these proxies for solar activity, but we kind of take a lot of shortcuts, right? We make a lot of assumptions. And it's not necessarily the right way to do it when it comes to really understanding how the sun works and understanding what type of activity we're going to see, especially when it comes to amateur radio, because you guys rely so heavily on solar flux. But really what you're looking at is only part of the story. Now, the other part of the other part of the story, the next part of the story, is what does this solar variability mean for solar cycle 25? Well, I'm sure you guys have heard how much harder it's gotten recently for us scientists to try to figure out what the solar cycle is doing, right? And it is tough because things are changing. The sun is not a light bulb. It's not something that has a light switch with a strict 11-year periodicity. It doesn't just flip and rigidly stay there for 11 years and then flip again and rigidly stay there. The sun is that lava lamp. It keeps changing constantly. And it's a quasi-11-year periodicity, okay, with the solar magnetic field constantly reversing orientation. You can see, you probably know this diagram with all the different solar cycles in there, and here's the average over a long period of time, and you can see the average really goes up and down. It's modulated by stuff. Well, really, you can say that activity increases for a few years around the field reversal, which is solar maximum, and then decreases again when the field becomes ordered, and that's solar minimum. But by doing that, you're really locking out a lot of the dramatic changes, especially the changes that are happening now, that are making things a lot more complicated and a lot more hard to predict. There are other competing cycles that cause deviations from 11 years, and they modulate the strength of the cycle over the long term. I'm sure by now you've heard the fear-mongering of the grand solar minimum. Anybody heard that? Maunder minimum, right? Run for the hills, right? Okay, no. Really what you're looking at when we talk about the grand solar maximum and the grand solar minimum, what we're talking about is that you still have this quasi-11-year periodicity, but it's going to be modulated a little bit more. There's an envelope now. So it makes the maxima a little bit higher, and it makes the minima not lower. You can't go lower than 0. It makes it more complicated, though, a lot more complicated, and I'll get into that in a minute. So when you go into these grand minima, let me rephrase that. The grand maxima makes the activity at maximum more or higher, and it makes the minimums less low. But in grand minimum, which is what we're in now, it makes the maxima smaller, and it makes the minima much more complicated. That's what I was trying to say. I said it backwards. But by using sunspot numbers as a proxy for solar activity, we're already missing part of that picture. And part of that picture is being explained a lot more by some of these faculae and these bright points now that are being excluded from the sunspot picture. And that becomes a real problem, and we'll talk about that. So where are we now? Well, recent solar cycles, since about cycle 22, have been showing the dramatic changes, making these predictions more complicated. I know I sound like a broken record here, but it's true. Basically, the entire space age, cycle 22 is, I don't know, the 80s, I think. I can't remember, I think it was 1980 was solar maximum for 22. That was really the peak of the grand solar minimum or grand solar maximum, okay? We had been, so essentially since 1950, when we really started launching a lot of these spacecraft and exploring, outer space as we know it, we were in a grand maximum. Well, sadly, since the 80s, we've been going into a grand solar minimum, and that's when our technology has really begun to blossom and explode, right? So we're becoming complacent because we think our star is very quiet, when in actuality it's not. The consensus, though, at least for right now, is that we're not dipping into another maunder, so don't worry, sunspots aren't going away anytime soon. We don't have to worry about solar flux dropping off the map. The cycle will be slower. We will have lower luminosity, so lower brightness, lower solar flux, lower activity at maximum, and this is consistent with the downward trend that we've been exhibiting since the peak in cycle 22. The current weaker magnetic field strength also means a higher cosmic ray flux that solar scientists, of course, don't talk about. But if our magnetic shield for our solar system is weakening because the sun creates it, then that means we get more penetration from stuff outside our solar system, and that's cosmic ray flux. The nice thing about it is that cosmic ray particle showers actually enhance radio propagation, just a little bit. It also enhances cloud cover, and terrestrial meteorologists aren't happy. And I get a few calls every now and again from sensitive radio, people who do radiation detection equipment, really sensitive stuff. They've talked to me and said, what can I do about this? Do we have good predictions for this? Because I'm having a hard time calibrating my equipment anymore because they're noticing even more cosmic ray penetration to the ground, which is pretty stunning, all things considered. So even as we go into these low cycles, there is a little bit of hope with cosmic ray penetration enhancing radio propagation to some degree. But the minimum is going to be in 2019 to 2020, but it's difficult to predict due to something called hemispheric asymmetry, and I'll go into that. But what this hemispheric asymmetry means, and this is a magnetic, again, everything I talk about is magnetic. What this means is that there could be a probability of much more, a higher number of extreme events during these weak cycles. Like I said, it makes solar minimum not smaller. You can't get smaller than 0, but it does make it more complicated. And that's where these extreme events can come in. And I won't go over this too much, but this is a prediction just to show you kind of how hard it was for solar scientists to make predictions. Back in 2008, they made a prediction about the cycle that we're in now, the cycle 24. They originally predicted that this cycle would have sunspots that were around 125 to 150, and that the maximum would be in 2012. When solar minimum didn't come, they revised it in July 2009. They pushed out the maximum to 2313 and dropped the sunspot number to like 100 or 75. And then when the sunspot minimum or the solar cycle minimum still didn't come, they made another prediction in 2011, pushed out the maximum to 2013 and a half, and dropped the sunspot number even more. What eventually happened was that we had a dual peak sunspot, a double maximum, and that's part of this hemispheric asymmetry. And the maximum ended up being late in 2014. So none of this was right. And so get ready, because we're still dealing with that, although we think we're getting a little bit closer now. So this was hot off the presses. These are the cell phone pictures that I took back, or that my colleagues took back at the Space Weather Prediction Center. I was hoping so desperately that we would end up having a decent a decent prediction, right? Because people have been kind of doing little predictions here and there for, I don't know, years. But really what you were hoping was to get more definitive than, oh, it's going to be like solar cycle 24. It's kind of like the cycle we're in, you know, and the minimum will be kind of between here and the next maximum, and, you know, sunspot number will be between this and 200, and, you know. So you were hoping that this would be a bit more definitive, and sadly, I was not thrilled. This is what it looks like. It's not your eyes, it's not your glasses. Nobody needs to adjust anything. This is the Space Weather Prediction Center saying, conservative. We're being extremely conservative. And I don't know about you, but I could basically just lift this and go, pa-tunk, and put it right there. Does this give anybody a warm, fuzzy feeling at all? No? Should I end the talk? No? No. Yeah, it's kind of the way I felt, you know. I'll go over the numbers, but I'll do it the way that it seems like it should be done, right? Timing of minimum 2019 and a half to 2020, strength of maximum 2023 to 2026. I mean, you know, come on. We knew this already, right? it's going to be another one like cycle 24. And that I believe, right? I don't believe any of these numbers are wrong, but it would be nice if we could narrow the box a little bit. Can we make these less pixelated, please? I really think what they did is they took this and they just blurred it. All right. So, feeling pretty much the way you guys do and being a little bit more punchy. And I'm not on the hook for this stuff, right? I'm not an official space or solar cycle predictor, so I can be a little bit more avant-garde if that's what it is. I went to my friends at NCAR and UCAR. Now, don't worry, I know this is extremely complicated. I will explain it, but there won't be a test, so you can snooze if you want. But this is where a lot of the good stuff is, so this is probably the slide I wouldn't snooze in. The reason why I went to NCAR and UCAR is because these guys have been looking at 400 years of solar cycle data, and what they've been looking at are not sunspots. They've been looking at bright points, the same stuff that creates the solar flux. And have they included just what's in the butterfly diagram? They've been including the polar faculae. They've been including lots of stuff. They've been including filament eruptions. They've been including all sorts of different data that exhibit some of the same patterns over and over and over, because they're all foot points. They're all proxies for that solar magnetic dynamo that's really taking care of everything under the surface. And you can find this data. This is online if you go to McIntosh et al. This is Scott McIntosh. He's the director of HAO at NCAR. Good friend of mine, dear colleague, and very underrated in terms of being a solar scientist. He also works with meteorologists and is really looking at really interesting things and seeing a lot of clues that terrestrial meteorology is telling us about the sun. So really frontline work. So what we're looking at here, let's talk about the top plot. This top plot is basically the sunspot number. Now, I don't know if you guys can tell the colors. Hopefully you can. The top line, this is the last 2 solar cycles. This top line is black, okay? And there's a lot of peaks in it. But there's 2 main peaks, one here and one here, okay? Those are the 2 dual humps of the previous solar cycle. Now, the black line here is the solar cycle, our solar cycle, 24, okay? And again, you see 2 main peaks, okay? This is getting into that hemispheric asymmetry I was telling you about. These guys actually pay attention to it, and they think they understand what's happening. Now, the lower lines, now I don't know if you can tell there's blue and red. The reason why there's a blue line and a red line is that they have separated out the North Pole magnetic pole from the South magnetic pole. And that's really important, because when you look at the sun and you think of the sun as this big magnet, it's really a system of little magnets that are acting in unison. They're trying to be like a dipole, but there's a bunch of little talking heads in there, and they all have a say. And sometimes they don't agree. And in this case, they don't agree a lot. What's happened at the end of this last cycle, I don't know if you can see, the blue and the red line kind of trace each other at the end of the last cycle. So they kind of were in unison. They kind of agreed a little bit, okay? But at the end of this last cycle, the red line, which is the southern hemisphere, went to 0 really early. And the blue line, the northern hemisphere, said, no, I'm not feeling it. I don't think I want to go to solar minimum right now. So the northern hemisphere, all the little magnetic poles in the northern hemisphere said no, and they hung out for another year or 2 before they finally decided to flip. And that's why the scientists kept saying, well, let's push it out a little bit further. Well, let's drop the next cycle and push it out a little bit further. This is why we had to keep doing the iterations. The southern hemisphere, its magnetic field just wouldn't leave, or excuse me, the southern hemisphere. It just wouldn't leave. It just kept hanging on. And that asymmetry between the northern hemisphere flipping and going through solar minimum and the southern hemisphere flipping, that asymmetry, it carried on through the next cycle. So now, if you see here, I don't know if you can tell, but you've got a red line that pops in the maximum right in here, okay? That's where that first peak is, and then it goes down. But the blue line doesn't peak till here. And that's the second hump. So basically what we're having with these dual peaked magnetic cycles is we have the northern hemisphere getting to maximum at a different time than the southern hemisphere is. They're not in phase. If you think of it as sine waves, right? You go to maximum and minimum. You can think of them in phase. In the big cycles, they're in phase. In the smaller cycles, not so. And that lowers activity, but it also creates very complicated structures, very complicated sunspots on the surface of the sun. Anybody remember September 2017? Of course you do, Nathaniel. You could give a whole thesis on it. Everybody remember Irma? Harvey, Irma, Maria? Remember trying to do amateur radio? Anybody work for races, RAs, Red Cross? I'm not hearing any groaning. I gave a keynote lecture back in October of that year, and the entire room was just despondent when I was telling them about what was going on. One of what we call a bad actor, it was a sunspot that was insanely horrid, and it was due to what we call hemispheric band compression. And what happens is when these hemispheres are out of phase, you end up getting magnetic layers that are opposite layers, kind of like icing on a cake, and they all compress together. So you get, in this case, if I talk about red and blue, you get red, blue, and they all squish together, and that's very dangerous when it comes to sunspots. It unleashed huge X-class flares, X-class flare after X-class flare, the biggest in the cycle, and it launched Carrington-class events. Okay? As a matter of fact, this past cycle, we had 2, if not 3, Carrington-class events. Only one of them clipped us. It clipped us, and the thing was launched the opposite direction. It's like I was pointing a gun this way. The sun launched it behind the sun's limb, firing a gun, and it still hit you. The bullet was so big, it still hit Earth, and it caused a storm. That's how big and monstrous these events can be. This is what we're dealing with these low solar cycles. And I'll talk more about that stuff in the antenna forum. But getting back to this. So now we're talking about hemispheric asymmetry. Well, here's the neat thing. This red-blue, this is that same magnetic field that we're talking about. Don't worry about it so much. Just recognize that this is that butterfly diagram. See how they're kind of like butterflies? Kind of like the butterfly wings? But now we've also got the polar stuff going on. So Scott and his crew, his team, have modeled not just what goes on with the sunspots, but also what goes on with the faculae. And they've done it for 400 years. Now here's the cool thing. These lines here, if you can see here, this is when that butterfly line for red starts. And look, it peaks exactly when this cycle peaked for the first peak. But look at the blue line. The blue line starts here. And look, it peaks again right there. So see how out of phase they are? There's red, there's blue. If this is time, that's almost 2 years, 2012 to 2014. And down here is the butterfly diagram for the bright points again. So he's looking at just this, in this case, he's just looking at the sunspots for the bright points. But what he's been able to do, his team's been able to do, is pull out what we call the terminator. These terminators are essentially when the butterfly diagram stops and then the new ones start. And those terminators have been able to realize that activity, once those terminators are reached, activity lights up like a Christmas tree. I mean really fast. And in fact, once you pass a terminator, you could see near a 100% increase in solar flux within a few months. Oops. So, well, I guess I can go back. One thing I didn't mention was that the terminator for cycle 24 to 25 is coming very quickly. By the end of this year, it'll be early, very early next year. That's what we think we're seeing. The nice thing is that once, even before we hit the terminators, we do start seeing activity pick up. So we could see sunspots begin as soon as late 2019, even though we're not in the new cycle yet. Activity does pick up before. Okay? Now, how fast will the solar flux change? Well, here's a couple examples. This is 1996 through 2020. Here's where the solar cycle started, right? And there's where the terminator was marked from Scott's team's result. And then here's another one here in 2011. So here's these two blown up. This is this region blown up, and this is this region blown up. if we look at it, you can see sunspot number. You probably can't read these numbers, but you can see sunspot numbers sitting here right around 70-something. And within a very short period of time, once we hit the terminator, that sunspot, or the sunspot number, the solar flux, sorry, the solar flux goes up outrageously. This is F10.7, not sunspot number, sorry. So it's sitting at the 70s, and then it goes up very, very rapidly. So here we're sitting at 100 already right here. This peak was at 110, and it just keeps going up from there. Look at this one. This is even more dramatic. This is 2011, so this is the current cycle now. We were sitting at about 70, 75, and then literally within just a very short period of time, we jumped up to 120, 130. I mean, it turns on like a Christmas tree. And here's even a better example. Here's 335 angstroms, so it's not the F10.7 flux like you saw in these other pictures here. But we take this little region and we blow it up. Literally, it jumps up 85% within 4 months. So once that terminator is reached, which could be very beginning of next year, maybe at the latest, we'll see solar flux jump up 100%. Okay? So how is the ionosphere affected by all this? Well, let me first remind you what the ionosphere is. It's a charged plasma layer above the atmosphere comprised of ions and electrons. And it would be neutral, but it gets charged from exposure mainly due to the sun's UV radiation, right, F10.7. But there are some transients in there, solar flares and things like that. But this charged nature facilitates radio propagation. But also, during active space weather, especially things like solar storms that we don't forecast in long-term predictions, the extra energy caught in the Earth's magnetic shield gets dumped into the ionosphere, and this energy will light up the plasma in the ionosphere, similar to a fluorescent lamp or a neon beer sign, if you prefer. Well, we don't have fluorescent lighting in here, but usually we do. And the result, of course, is the aurora, the northern lights, or the aurora australis, the southern lights, along with changes in radio propagation. So on top of the solar variability, on top of solar flares, on top of sunspots, on top of all of this stuff, we also have space weather effects. And that's just the beginning. Space weather enhances an already very complicated system. So before I go into that a little bit in more detail, let's talk about ionospheric layers in a slightly different way. I'm sure from a lot of the books and things that people read, you don't necessarily talk about ionospheric layers from the point of electron density. And I'm going to kind of show you more of a scientific way that that ionospheric scientists label these layers. What you're looking at is the daytime ionosphere and the nighttime ionosphere. You're looking at electron density going up on both, starting at 0 and going up. And you're looking at altitude going up on the vertical. Okay. So here's, of course, the D region. You see the way they're kind of laid out, the D, E, F1 and F2 layer on the day side. And they're just kind of these flat, painted surfaces, right? Real simple, pretty much what you see all the time. But with scientists, what we do is we actually trace out over over altitude range, we actually trace out this electron density. So the layers look very different from plots that we use. And really why we do this, well, not why, but one of the reasons why we do this is that it illustrates the fact that there are competing processes going on all the time. When you look at the ionospheric layers, you see that the layers, like the E layer or the F1 and F2 layer, this is where you find peaks in the electron density, right? It's not like electron density only exists here, only exists there, but this is where it peaks. Why does it peak? Well, there's a lot of atmospheric chemistry going on, okay? There's a lot of different competing processes. There's processes that are trying to rip apart the molecules and make them charged, like the sun's UV radiation. There's also chemical processes that are happening. But then there are also, as you go up in altitude, a lot of other changes that just associate with going up in altitude, like the species change. The dominant species change in the air. The height, the density of them, just the neutral density changes. And the atmospheric chemistry itself then, because of that, changes. So what happens is that you get here at these peaks, what the dominating process is ionization. So you get a peak in this electron density here. But as you continue to go up in atmosphere, up in altitude, the ionization actually begins to lose, and recombination wins. So you get kind of a trough And then the species change again, the densities change again, the chemistry changes again, and you begin, and ionization wins again. So you get another peak. And this continues as you go up and up and up and up, okay? So you think of it, 3 minutes? Oh, okay. Okay. So you go up in altitude, and these competing processes make a huge difference. Now, of course, at night, you don't have the UV radiation, so, of course, the layers change, right? They change dramatically, but it's the same kind of idea still. Now, in time, you also have the issue with daytime and night. You have the issue with daytime and nighttime, but you also have this third region, the gray line. The gray line is really a region because you're having things collapsing, right? And having a lot of changes all at once. And I'm going to skip through this. The reason why is because if you pull out into outer space, you have to realize that it's the same kind of issue with these layers collapsing that you have on the ground when you have already witnessed sundown and you look up at the sky and you see a plane and the plane is still in sunlight, right? And you realize there's still sunlit, but the sun is already set for me. Same thing happens with the layers. As you go higher in altitude, you can see further over the horizon. So the sun hasn't set for these layers up here, even though it's set for the D layer. So it doesn't make it a gray line, it makes it a region. And that's also what part of the magic is. So imagine all of the atmospheric chemistry changing, the temperatures changing, all of this stuff happening all over the place over a very extended region. And this is part of the reason why you're able to get propagation sometimes from the northern hemisphere to the southern hemisphere, but it never is stable. It's because this is happening all the time as you rotate through it. Now, space weather effects on propagation, of course, make it even worse, but now you get stuff from underneath. Imagine with the ionosphere, not only do you get space weather from above, but now you get things like atmospheric heating instabilities that can cause plasma bubbles. You can get waves and winds in the neutral regions. All of this stuff starts making these things undulate, almost like when you see waves with clouds, right? You can see these undulating clouds. The layers do the same thing. So the ionosphere really has the problem of being attacked both from above and from below. And I have to say to Jerry, K8VGL, Jerry, where are you? There's Jerry. Everybody thank Jerry. He's the reason why this plot is in here. He's a VIP member of my steering committee for my Patreon project, and he suggested that I put this slide in. And I think it's a fantastic way of getting you to understand that the ionospheric weather ballet is incredibly complex. You can see there's a ton of complex processes. I won't even go through it, but here's some: gravity waves, solar-driven tides, fountain effect, plasma plume, equatorial anomaly. You get neutral wind, which drags up the ionosphere. You get a downward driven flow. You get particles propagating in. You get all the auroral stuff, heating and currents. You get so much stuff going on all the time. Some of it driven from below, some of it driven from above. So because of this, coupling to the neutral atmosphere, driving these microprocesses that are not well understood or characterized, and terrestrial weather can complicate these interactions. You can have a hurricane. They drive sprites and jets up into the upper atmosphere that affects these ionospheric layers. Then you also have from above, you have coupling to the Earth's magnetic shield that can cause particle precipitation coming down. So the poor ionosphere is getting hit from both ends, and it's got to deal with this. So really, what it comes down to is that until models improve, things like the WSPR and the reverse beacon network activity remain among the most robust ways of probing the ionospheric, real-time ionosphere for radio propagation. And so it goes beyond just, let's try to keep doing this, it goes beyond just solar and space weather and the sun's variability and everything else. So please keep that in mind as as you look at radio propagation. The solar report, as much as I'd love to tout it for obvious reasons, is not the only thing that makes the ionosphere work. So to conclude, here are the very illuminating predictions from the Space Weather Prediction Center. We do know that cycle 25 will be another low activity cycle, but that does not mean activity stays low. I will talk more about that in the antenna forum. The hemispheric magnetic asymmetry, hopefully I gave you a better idea of what that is the main reason why prediction remains blurry. So don't expect the Space Weather Prediction Center's predictions to get good until after solar minimum happened. And they'll go, oh, there it was. Aren't we good? We're good, aren't we? We're good. It's right there. But we do believe that solar activity will probably pick up at the end of 2019 with the terminator, e.g. solar minimum, if you look at it as a point, not a phase, and there's still debate which way you should look at it, will be reached hopefully by early 2020 if Scott and his team have successfully sussed out 400 years of data. And once the terminator is reached, the solar flux will rise quickly. However, Earth's ionosphere has a complicated weather system. Thank you, Jerry, for making sure we all knew that. That was very critical. And the dynamics includes much more than just solar activity. So the coupling both above and below make a huge difference. And I'm hoping that ham-psi will help. Nathaniel, you're not paying attention. Oh, okay. I'm hoping that ham-psi is going to help get the ionospheric scientists to pay more attention to this and how desperately it's needed. Because the ham radio, community really needs help from the ionospheric side to understand better how radio propagation works. So.